Okay, the second paper is Nüwa. The speaker is Li. He is a master student at Xi'an Jiaotong University, advised by Professor Peng Zhang. Please.
Good morning, everyone. My name is Li, and today I'm excited to present Nüwa, efficient generative control plane for AI network simulation. This is a collaborative work between Xi'an Jiaotong University and Microsoft Research. AI training involves a vast data space. The parallel strategies like TP, SP, EP, PP, DP, and transport protocols like DCQCN, HPCC, and PFC, and network topologies like Cloud, Torus, Dragonfly, and UBmesh. Testing this on real hardware is extremely costly. For example, running a 10,000 cluster for one day can cost over $1 million. And simulations offer a flexible and cost-effective way to explore new design and tune parameters before real-world deployment. An end-to-end AI training simulator framework consists of several key components: a workload generator, a training framework simulator, computation simulator, and the collective communication simulator. Underpinning all of this is the network simulator, which simulates the underlying communication traffic. Most AI training frameworks use a discrete event simulator, or DS, for network simulation. DS models packet-level behaviors with high fidelity, making it a preferred choice for accurate simulation. However, DS is slow. Simulating a single iteration at a 1000 GPU scale can take days. And GPU is the main bottleneck in AI training simulations due to its inefficiency. Let's take a closer look at why network DS is a bottleneck. DS has two stages, initialization and execution. Initialization involves building the topology and computing routing tables, often by simulating real-world routing protocols such as BGP and OSPF. Execution handles packet-level events like sending, queuing, forwarding, and receiving. Recent work has focused on improving parallelism in execution stage. DONS uses data-oriented design. Unison applies fine-grained partitioning and load-adaptive scheduling. CMI uses lock-free global variable sharing, and Multiverse leverages GPU for acceleration. We found that the control plane significantly affects simulation efficiency. It introduces high computational overhead, high memory consumption, and inefficient routing table lookup. These problems are orthogonal with previous work that's targeting improving parallelism at execution stage. As this figure shows, the initialization time is in a standard simulator S3 is unexpectedly long. For factory topology with 8,000 GPUs, it takes about 5 hours to compute the routing tables. And for a larger scale, it cannot finish within 1 day. Some tools like S3 Data Center have introduced optimizations to speed up the routing computation. However, even with these improvements, the performance is still insufficient for the scale of modern AI clusters. The second major issue is memory consumption. The memory used to between routing protocol states is hard to measure, so we just measure the memory used to store routing tables in S3. Since the experiments involving 16,000 and beyond, 16,000 GPUs and beyond cannot finish within 1 day, we provide an estimated results. Based on our estimation, storing routing tables for a 27,000 GPU cluster would require nearly 200 gigabytes of memory, posing a significant challenge to simulation scalability. Inefficient initialization also slows down the execution stage. The large routing tables lead to inefficient cache usage during the packet forwarding process. Our analysis shows that in S3, the time spent simply looking up the next hop in the large routing tables can account for over 97% of the total execution time. This brings to our key insight. The AI training clusters typically adopt highly regular and structured topologies like clause, dragonfly, and UB mesh. And the routing policies are relatively simple, typically shortest and nearly shortest path with simple policies. And this combination results to highly regular and predictable routing patterns, such as the up and down routing in closed network. So our idea is, instead of simulating complex protocols to compute massive routing tables, we can replace the tables entirely with simple routing rules. Based on this insight, we designed Nüwa. On the right is the architecture of Nüwa compared to a traditional DS on the left. Nüwa replaces routing tables with a generative approach. It uses generation rules to build topology, and then hierarchy addresses, and generates routing rules to forward packets, which eliminates the need for routing table lookup. Let's walk through how Nüwa works with a fast tree prototype. The user provides topology generation rules, which defines the structure and connections. Then Nüwa assigns hierarchy addresses to each node and generates the routing rules for packet forwarding. The figure compares the initialization time of Nüwa against the vanilla S3 and optimized S3 data center. For 65,000 GPU cluster, where S3 cannot finish, S3 data center takes several hours. Nüwa takes only 21 seconds to complete the initialization, which is 1,000 times faster than S3 data center. Here we see the execution time for all reduce and auto traffic patterns. While S3 struggles to scale, cannot finish on a 3,000 GPU cluster, Nüwa consistently outperforms S3 data center, achieving up to 20% speed up in the execution stage. The table shows the lookup time during execution. By eliminating large routing tables, lookup in Nüwa is 200 times faster than S3 data center, nearly negligible. This is due to our lookup-free forwarding method, which also improves caching efficiency. We plan to extend Nüwa to support other topologies like Dragonfly, UB mesh, and support other simulators such as APNet++ and Bounce. We also plan to simulate failures in network and make Nüwa open source. In summary, control plane initialization is a major bottleneck in network DS. Nüwa addresses this by replacing routing tables with high-level routing rules, achieving faster initialization, lower memory usage, and improved execution speed. Thank you for listening. I will be happy to answer any questions.
Nice talk. So one quick question. So if we use packet spraying, so then we don't have to compute the routing tables, right?
I think packet spray also needs some information to get their forwarding because they need to find the paths.
Okay.
Okay, thank you.